In this video, we'll do a more advanced example of using EQR opgenesis. In this case, we'll design a diplexer. The individual channels of the diplexer are described by Combline equivalent circuits. It looks like this, somewhat simplified. And we join them together at the top level schematic using two transmission lines to a common junction. This transmission line rotates the response of this filter to an open circuit in the passband of this filter, and this transmission line rotates the response of this filter to an open circuit in the passband of this filter. So this is probably the simplest way to design a microwave diplexer. And if we change the electrical length of those two transmission lines, you can see how the response of the overall diplexer changes. And in fact, there is no unique solution for these transmission line lengths. We can optimize this to a useful diplexer using any one of these potential solutions. But as it sits, this is a very good starting point for our optimization. And these are the responses of the individual channels. We start with doubly terminated designs. In classical filter theory tells you that you need to synthesize singly terminated designs for a diplexer, but in fact that's not true. We can do this strictly with optimization. So if we start the optimizer, we want to tell it to look at all the schematics, and our top level schematic is schematic number 3. And if we hit the optimize button, and in just a very few iterations, here it's a total of 4 iterations, we have an equal ripple response in both passbands of our diplexer. Since both channels are n equal 5, there's 10 variables for this channel and 10 variables for this channel, so we're optimizing a total of 20 variables simultaneously to do this design. And if we look at the individual channels, now they're on a 50 ohm basis at input and output. They're distorted because we've had to modify the element values of the filters in order to get to the diplex condition here. Now you'll notice that our isolation or rejection, say here at the passband of the upper passband of the lower channel, is about 40 dB. What if we need more than that? Well, we can add resonators to this channel, or we can add a cross coupling and form a transmission zero here on the low side of this filter. And if we look at the schematic for that filter, I've put a capacitor in place here. Right now it's 0 picofarad, but there's a capacitor between resonator 2 and resonator 4. This is what we call a cascade triple, and this capacitive cross-coupling will give us a transmission zero on the low side of the filter. So let's increase the value of that capacitor, say to 0.005 picofarad, and of course we detune our passband here, so we need to restore that back to equal ripple. So we rerun the optimization. And we're back to perfectly equal ripple here. And we've increased our rejection here a little bit, the zero is out here in the stop band, and we're gradually going to walk it in closer to the pass band of this filter. So let's increase this one more time, say to 0.1 or 0.01 picofarad. And again, we've detuned our pass band, so let's bring it back to equal ripple. And now we're clearly maybe greater than 50 dB here, where we had more like 40 dB before. This is clearly getting steeper. And if we make one more step here, we'll actually see the transmission zero appear. And actually there it is. And you can see it here in the single channel response and here in the diplexer response. And we just need to re-optimize. And now we're done. Again, we can clearly see the transmission zero here. We can clearly see it here. And now we're down to about 60 dB rejection instead of 40 dB rejection without adding any extra resonators here. We could do the same thing on the lower channel, but to put a transmission zero here, we need to add an inductive cross-coupling between 3 resonators in that channel. So what we've done here is we have the beginnings of a cross-coupled filter diplexer without resorting to a coupling matrix synthesis. We've done it purely by optimization. And this is, in fact, a very simple and efficient technique when you have the robust optimization that we have in EQR Op Genesis.